Dear students, welcome to another lecture on mechanics of solids. In this lecture, we would be starting with Module 3 topics. The Module 3 is all about drawing what is known as the bending moment diagram and the shear force diagram. So, in this discussion, we would be confining our discussions to three types of beams. So we will be discussing statically determinate beams only, and the different types of statically determinate beams that we will be discussing is one is a cantilever beam. So this is a cantilever beam. The second type is we would be discussing will be a simply supported beam. So this is a simply supported beam, and the third category that we will be discussing is will be a beam with overhang. So this is an overhang. So this is a beam with overhang. This may also be of this type wherein you have overhang on both the sides. So this are the different types of beams that we are going to discuss. Now another thing that we have to discuss regarding our discussion is the types of loading that we will be considering. So the different types of loading that we will be considering is, first one is concentrated load. Now what is this concentrated load? So concentrated load is again an idealization, simply means that it is an assumption, and it means that if load is transferred to a very small area, then we call it as a distributed load. That means if the area of transferring of the load is a very small area, then we will call it as a a concentrated load. Examples of concentrated load are the support reactions of beams and columns. Support reactions of beams and columns are examples of concentrated loads. Next is the another type of loading that we will be considering is uniformly distributed loading. Uniformly distributed load. Now this means that the intensity of load is same. Okay, uniformly distributed load means the intensity of the load is the same. There are two types of uniformly distributed load. First one is a line load. Okay, that means the load is distributed along a line. Example is wall load. Okay, wall load. Imagine that we have a beam and the beam is supporting a wall. So let the thickness of the wall be 30 centimeter and let the height of the wall be 3 meter. The unit weight of wall is 20 kilonewton per meter cube. So if we want to find the load that is distributed per meter length of the beam, then all we have to do is we will take 1 meter of the wall. If we take, what is the load of this 1 meter? Okay, if we calculate the load of this 1 meter, the load that is acting on this 1 meter will be equal to the volume into this specific weight. Volume is 3 into 1, that is length into breadth into height, that is 0.3, which is the thickness, multiplied by height into the length we are considering as 1 meter, into the specific weight, that is 20 kilonewton per meter cube. So we will be getting it as 18 kilonewton per meter. So the wall load per meter will be 18 kilonewton. So if you can represent it as in this manner. Okay, so this is the way in which you represent a uniformly distributed live load 18 kilonewton per meter. Another way of representing it is in this manner also. You may represent a uniformly distributed load. So basically what you have to remember is uniformly distributed line loads will have a unit in kilonewton per meter. Okay, it is distributed surface load. Now when we say surface load, it means that it is distributed over an area. Okay, example of surface load is floor load. So imagine that we have a floor slab. Imagine that we have a floor slab, and let us say the thickness of the floor slab is uniform. The floor slab is having a uniform thickness. That means at every point of the floor slab, the weight that is going to act on the floor slab will be the weight due to the thickness of the floor slab. That means the self weight of the floor slab. Similarly, whatever load that is going to come, for example, on top of the floor slab, you will be having floor finish. Floor finish also will be uniformly distributed over this whole area. Therefore, the weight that is going to come over the floor slab will be uniform, or will be having the same value. So what we will be doing is, instead of taking in the earlier wall load case, the wall was distributed along a length. However, here it is distributed along an area. So since it was distributed along length, we considered per meter length of the wall. So here we will be considering per meter square. So we will be taking a 1 meter square stretch. Okay, a 1 meter square area we will be taking, and we will be considering what is the load that is going to come over it. Again, if for example, let us say the thickness of this slab is 20 centimeter. Okay, that is 0.2 meter. So if you want to calculate the load that is coming per meter square, all you have to do is load per meter square is equal to volume will be thickness multiplied by the area we are considering is 1 meter square. So this will give you the volume multiplied by the density of concrete, I mean the specific weight of concrete. We are assuming it as 25 kilonewton per meter cube. So if we try to do the calculation, we will get it as 5 kilonewton per meter square. Okay, so this is the area that is distributed. So that is uniformly distributed surface load. Okay, now another category of load that we have to discuss is known as uniformly varying load. Uniformly varying load. So this is another category of load that we have to discuss. Okay, so different types of uniformly varying load exist. For example, imagine that you have a wall that is constructed below the water. Imagine that there is a swimming pool. Let us consider a swimming pool. So this is a swimming pool. You have walls on the four sides, and it is filled with water. Now if you try to calculate what is the water pressure that is going to act on this particular vertical member, the water pressure will be having a triangular variation. That is, the intensity will be increasing from the top to the bottom, and this intensity will be gamma multiplied by the height. Okay, so what you can see is that the intensity of load is 0 here, and it is linearly increasing downward. So this is known as uniformly varying load. One example of uniformly varying load. Another example can be, for example, imagine that you have a sloping roof. Okay, so we have a sloping roof. So this is the roof, and let us say this much portion is being filled by masonry. Okay, so now if you try, if when you had a rectangular or a masonry having uniform height, you had uniformly distributed load. Now since the masonry is having a triangular variation, similarly the load that is going to come over it is also going to have a triangular variation. So you will have a load distribution like this, and you can represent it by the maximum value of the load intensity. Similarly, imagine if the roof truss was like this and this much portion was filled by masonry. In that case, you would be having a triangular variation of the load like this. Okay, so there are different ways in which loads can be represented. So having understood the basic type of beams and the loads, let us go into the main topic of discussion that we are having, which is bending moment and shear force. So to understand what is bending moment and shear force, the first thing we have to understand is, imagine if we are having a member like this, and if you are applying a tensile, a force along the uh, longitudinal axis, then you will call it as an axial force. Okay, force, when the force is applied along the longitudinal axis, you will be calling it as an axial force. Now if the force is applied to a member uh, in a direction that is perpendicular to the longitudinal axis, you call this as transverse loading. And we have already studied in our engineering mechanics that beams are members which are subjected to transverse loading. And now when the beam is subjected to transverse loading, what is going to occur is the way it is going to bend is a bit interesting thing to note. Um, Imagine we have a beam like this. Okay, so under the loading, what is going to occur is it is going to bend. So under the loading, what is going to occur is it is going to bend. Now what's going to happen in reality is, um, you will see that the portion below the beam is going to undergo some sort of stretching. That is, you will see that if you keep on bending it, you will see crack formation occurring on the bottom. So in when the beam is undergoing a sagging deformation, what is going to occur is, the member, I mean, what we will assume that, let us say if we have a beam like this, we will assume that this beam is made of infinite number of longitudinal fibers. Okay, we will assume that the beam is a combination of infinite number of longitudinal fibers. So if you are having a rectangular beam, we will consider the rectangular beam as a combination of infinite number of longitudinal fibers stacked one above the other. Now when this bends, what is going to happen is, we can observe that some of the fibers which are towards the bottom are going to undergo tension, whereas the ones which are on the top are going to undergo compression. So if you this that means there is a transition from the maximum tension will be on the fibers at the bottom and the maximum compression will be on fibers at the center. That means in between there is going to be some sort of a point wherein the fiber is not at all stretched. So there will also be a fiber that is not going to be stretched at all. Okay, basically what I want to tell you is, some of the fibers, when a beam bends, some of the fibers are going to undergo are going to experience tensile stresses, whereas some of the fibers are going to experience compressive stresses. Okay, so if you try to take the cross section of this particular beam, if you try to take the cross section, what you will see is that there will be a line on the cross section where the stress will be zero. Okay, and above that the stress will be compressive in nature, and below that the stress will be tensile in nature. Okay, now the resultant of these stresses, in addition to the tensile and compressive stresses, there will also be shear stresses that will be developing in the structure. So basically, when a beam is subjected to bending, it is going to develop shear stresses as well as this combination of tensile and compressive stresses due to bending. Okay, now let us try to introduce a concept known as stress resultants. In every cross section, there will be in general three stress resultants. One is known as normal force, which is the resultant of the normal stresses. Second one is known as shear force, which is going to be the resultant of the shear stresses. And the third one is known as bending moment, which is the resultant of the bending stresses. Okay, you are going to have three stress resultants. One is, so these stress resultants, these are the stress resultant at every cross section. Okay, these are the stress resultant at every cross section. There is going to be a normal force, which is the resultant of the normal stresses. There is going to be shear force, which is going to be the resultant of the shear stress on the cross section, and there is going to be bending moment, which is going to be the resultant of the bending stresses. Now we also need to develop some kind of a definition for these three. So basically normal force means it is the internal resistance to longitudinal deformation. Similarly, shear force is internal resistance to shear deformation, and the last one is bending moment. So that is again internal resistance to bending deformation. Okay, so these are the different types of uh, shear force, bending moment, as well as their definitions. Now what we have to do is we need to develop a relationship between the shear force, bending moment and the loading. So relationship between shear force, bending moment and loading. So what we will be doing is, let us consider a beam that is subjected to some arbitrary loading. So intensity is varying, the loading is arbitrary. Okay, intensity is varying, and we need to consider to find out what is going to be the relationship between shear force, bending moment and the loading. So since it is varying, what we are going to do is we are going to consider some section at a distance x from the left end, and we are going to consider a small strip of length delta x. Okay, so in that region delta x, we are going to assume that the loading is uniform. So we will try to draw a zoomed in figure of the same. So if you try to draw a enlarged figure of that delta x region, the region is going to look like this. So this will be the region of length delta x. Okay, the loading that is going to act on it, we are going to assume that in the region delta x the load is uniform. Let us call it as having an intensity W kilonewton per meter. Okay, now let us assume the shear force and bending moment as being positive. So the sign convention is sagging moments, we will assume them as positive, and we will assume shear force as positive if it rotates the segment clockwise. So here the bending moment, let us say it is m. As it moves a distance delta x, let us assume that there is an increase in the bending moment by delta m. So these are merely assumptions. Similarly, let us say the shear force here is v, and as it goes to the a distance delta x, let us say there is an increase in the shear force by delta v. Now this is a segment of the beam, and if the beam is in equilibrium, then this segment of the beam should also be in equilibrium. So what we are going to do is, let us evaluate the equilibrium of the beam. So if we go for vertical equilibrium, what we are going to see is v is acting in the upward direction, minus v plus delta v is acting in the downward direction, minus w into delta x is also acting in the downward direction, is equal to 0. So what we are going to get is v and v are going to cancel. We are going to get delta v by delta x is equal to minus w. Now if you apply the limits as delta x tends to 0, we will get a relationship as dv by dx is equal to minus w. So what this means is that the rate of change of shear force is equal to the slope of the shear force diagram is equal to intensity of loading, negative of the intensity of loading. Okay, so this is the physical interpretation of this particular equation. So that is the first relationship between shear force and the shear force and the intensity of loading. Now what we will be doing is we will again try to develop another relationship between the bending moment and the loading. So what we will be doing is, let us take moment about the point O. Okay, so if we take moment about the point O equal to 0, so m minus m plus delta m plus v plus delta v into delta x plus w into delta x the whole square divided by 2 equal to 0. Now what we can see is delta x is a small quantity, so square of that will be equal to 0. Similarly, this term delta v into delta x is also a very small term and can be neglected. So if we try to rewrite this equation, what we are going to get is delta m by delta x is equal to delta v. This is what we are going to get. Is equal to v. If we apply the limits, we will be getting dm by dx is equal to v. So this is the second relation that we are having. Again, this equation can also be interpreted as the rate of change of bending moment is equal to the shear force. It can also be interpreted as the slope of the bending moment diagram gives you the shear force. Okay, so there are different ways in which you can interpret it. Again, we can substitute this value in the previous equation that we have found out. So instead of v in the previous equation, if you replace this, you will be getting another equation, d square m by dx square is equal to minus w. So you can also get a third equation like this. Okay, so basically when we say a relationship between bending moment and shear force and intensity of loading, we mean these three equations. dv by dx is equal to minus w, so that is our first equation. dm by dx is equal to v, this is our equation number 2, and d square m by dx square is equal to minus w, this is our equation number 3. So these are the relationship between, okay, uh, bending moment, shear force and the intensity of loading. Again, what we have to understand here is these have physical significance. They represent the rate of changes of the shear force, bending moment and bending moment. Okay, or if you want to put it in another words, they represent the slope of the shear force diagram and the bending moment diagram. Now let us try to understand what is this shear force and bending moment diagram. Okay, so these are diagrams, okay, whose ordinate gives the intensity of shear force or bending moment at that location of the beam. Okay, so shear force and bending moment diagram are diagrams whose ordinate gives you the intensity of shear force or bending moment at that particular location of the beam. For example, let us say we have a beam subjected to a concentrated load, okay, and the bending moment diagram is drawn like this, and the shear force diagram looks something like this. Okay, so this will be the shear force diagram. We will try to see how to draw this, but basically what I'm trying to explain is what the shear force diagram. It means that the ordinate here for the bending moment diagram is 0, which means that the bending moment at this location of the beam is 0, and we know that it is a end hinge and the bending moment will be 0. Similarly, the bending moment is maximum right below the concentrated load, and that is at the center. Okay, and at any intermediate point you can also calculate the bending moment by knowing that the variation is linear. Similarly, in the shear force diagram, if you look, you will see that the bending moment is varying as a constant. There is not much variation in the shear force diagram, and there is a sudden change in the shear force diagram at the point of the loading, and then it goes to negative. Okay, so we will try to see understand what is this positive and negative for the shear force and bending moment diagrams. But basically I wanted to you to understand what is the idea of the definition for the shear force and bending moment diagram. Also, let us try to evaluate the different relationship between the loading and shear bending moment diagram that we have developed. So if you look, first relation was dv by dx is equal to the negative of the intensity of loading. If you look in this particular region, the intensity of loading is 0. So dv by dx is equal to 0. So when the slope is 0, it means that the line is a horizontal line. So you can see the shear force diagram is having a horizontal line here. Similarly, the shear force diagram is having a horizontal line here also. Okay. Also, if you try to see uh, again, if you see at the point of the concentrated load, okay, so at the concentrated load, if you try to see dv by dx, dv by dx means it is the intensity of loading. It has to be in kilonewton per meter. Now this is a concentrated load, that is kilonewton. So if you convert it into kilonewton per meter, this will become an extremely high value. That means it will become some infinity. So if the dv by dx is infinity, it means that the line is a vertical line. So at times of the concentrated load, there is going to be some sort of discontinuity in the, whenever there is a concentrated load, there is going to be a discontinuity in the shear force diagram. Again, dm by dx, if you try to put dm by dx is equal to v. Okay, dm by dx is equal to v. So if you look, dm by dx is equal to, shear force is having a constant value from here to here, that is, it is constant. So slope is constant. If you look, when the slope is constant, it is going to be a straight line. Slope is constant, it is going to be a straight line. Similarly, dm by, and also it is, the slope is positive here. When the slope is positive here, the line will be in this direction. For example, a line like this is having a positive slope. Once it reaches this particular point, there is a discontinuity, and after that what you will see is dm by dx is equal to minus v. Again, it is a constant value indicating it is a straight line. The bending moment is a straight line, and there is a negative sign indicating that it is going to slope downward. Okay, so this is how you evaluate the shear force and bending moment diagram and their relations. Okay, so hope you have understood it. Now what we will be doing is we will be seeing some examples on how to draw shear force and bending moment diagram for different um, cases. Okay, we will discuss that in the next lecture. Thank you.